Okay, now post tension axial members. Now, in post tensioning, because now I have the jack that is already there in the system, as the concrete is shortening, I can apply more force, right. So, typically the elastic shortening as it happens, then it is already accounted by applying more force. So when in post tension system, let us say if you have only one cable and then you stress them, as you stress them the concrete will shorten, then you can apply more stress to the level what you want, right. So then there is no really loss in a post tension member if all the tendons are stretched simultaneously. However, if in case of a post tension axial members, if you have more than one tendon, then if the tendons are stretched sequentially, then there is a loss in tendon due to the subsequent stretching of the other tendons. That means, if all the tendons are stretched simultaneously, there is no elastic shortening because the jack is already there, and as the elastic concrete is shortening, you apply more stress to the level what you want. However, when you have stretching that is happening in a sequential manner, let us say first one I do, then I put the anchors, then the second one when I do the stretching, the first one is already anchored, that will undergo some elastic shortening. So, when you do this stretching in a sequential manner, you will have loss in the tendons that were stretched before and anchored, okay. Not the one that you are doing stretching, but the tendon that was stretched before and anchored will have elastic shortening loss, right. So, that is what we see. So, the loss in each tendon can be calculated in a progressive sequence, or we can also do an approximation to calculate the loss in this case of a post tension system. Now, typically what we do is the loss in the first tendon is evaluated precisely, and half of that value is actually used as an average loss for all the tendons, okay. So, that's exactly, let us say you have 5 tendons or 5 strands, and then what you do is because of the sequential stretching, you calculate for one tendon precisely, and then you take half of that value, and that would be, then you add them up, then that becomes your actually the total loss due to elastic shortening. So, this is what we are doing. So, okay. So, now you can see that this is half of delta into Fp1, which is the loss in the pre-stressing for the first cable. Now, this is again can be written as m into Fc1. So, you can add them up. Let us say you have n number of tendons. When you have n number of tendons, the nth tendon when you do it, that nth tendon will not have any loss happening because of the elastic shortening, but before that n minus 1 tendons will have losses. Now, that you can approximate that by this kind of a summation, right. So, that is what we do it here. Okay, now let us go to the post tension bending members. In post tension bending members, as you can see that because it is a bending member, typically the cable profile will be parabolic like the one that you see here, and this is the cable profile CGC and this, and the calculation of loss for the tendons is basically similar to what we did for post tension axial members only. In curved profile, the eccentricity of the CGS and the stress in the concrete at the level of CGS will vary along the length, right. Why would it vary? Because the pre-stressing moment is going to change, right, because if I take at this location, my eccentricity is this. If I take at this location, my eccentricity is this. So, at each section, because the cable profile is changing, the pre-stressing moment is also changing, right. So, we have to now calculate an average stress in the concrete, because depending upon the cross section that you are doing, your stress is going to change, right. So, you have to calculate an average stress. Now, how do we do that? So, this is what we do. For a parabolic tendon like the one that you see here, let us say at the midpoint you have Fc2, you calculated the stress in the tendon, right. And at the support, let us say you have an eccentricity small e, and then you have a stress of Fc1. So, now we know that because the cable is having parabolic, the average stress in the concrete is also going to be Fc1 plus 2/3 of Fc2 minus Fc1, because Fc2 is going to be higher. Why? Because higher eccentricity of the pre-stressing cable, right. So, in this way you can take an average stress in the concrete along the length of the member. That average stress can be used for calculating the pre-stressing loss due to elastic shortening in a post-tension bending member. Now, how do we do that? I think we can also do a more rigorous analysis by actually calculating the strain, right. Now, how do we do that? So, this is what we do. We evaluate the strain in the concrete at the level of the CGS accurately from the definition of strain. So, from the first principle what is the definition of strain. So, using that we can actually calculate the variation of strain along the length of the member. Now, let us say you have a beam with two tendons and they are, so again when you have two tendons, if both of them are getting stressed simultaneously, there is no elastic shortening. Only when you do it sequentially, when you do the second one, you will have loss in the first one. So, that is what we are looking at with an example. Let us say that I have this kind of a beam. Let us say I have these two tendons, the first one is tendon A, another one is a tendon B, and you can see that the eccentricity is also different for different tendons, right. So, let us say the tendon A first I have stretched and I have anchored them. Now, when I do the stretching for the tendon B, what will happen? There will be elastic shortening that will be happening at the level of tendon A, that we have to account for that. So, let us see now how do we derive the loss that is happening because of that. Now, you see this is the axial strain definition which is from the normal component, and the bending strain component that is happening because of the pre-stressing moment that you are applying. Okay. So, this comes from your normal component which is your, let us say, Pj by A divided by Ep, and this comes from pre-stressing moment. Okay. The moment will, this is from moment, this is from normal force. Okay. This is stress divided by elastic modulus will give me the axial strain, right. So, let us look at that. Now, these are the schematic, this is CGC of the cross section, and these are the two cable profile, and the one that is in the dark brown color is basically your tendon A, and the blue color is your tendon B. Now, what we are doing is we are also defining the cable profile. At the support I am calling that as 1, okay. You have eccentricity of the cable A at support is EA1. Similarly, for cable B is EB1, and then you can at the midspan again for the cable A it is denoted as EA2, for cable B it is denoted as EB2, right. So, in this way we can define the variation of your eccentricity of this cable as a function as EAX for cable A and as EBX for cable B, right. So, this is again simple parabolic equation. So, we know for a parabolic equation cable profile, depending upon the eccentricities of the cable, we can write the EAX for example for cable A as EA1 plus 4 into delta EA times x by L into 1 minus x by L, where x I am taking it as you can see here from this length at any distance x. If I give a number, then I can get the eccentricity at that distance x. Now, what is delta EA? Delta EA is nothing but EA2, delta EA is nothing but EA2 minus EA1. Okay. So, similarly for the cable profile B, the eccentricity at any distance x can be written as EB1 plus 4 into delta EB into x by L into 1 minus x by L. Again delta EB is nothing but EB2 minus EB1. Okay. So, in this way we have written that. So, you can get the cable profile equations. Now, let us look at it from first principle. What is the stress in the delta FP? We know that it is EP into epsilon C, right. So, EP into epsilon C. Now, the strain we can decouple them into two components. The first one, epsilon C1, is the strain due to axial force at the level of tendon A. Now again, we have two tendons. When you are stretching the tendon B, you will have loss that is happening only in tendon A. Because it is a bending member, you have a curved profile, you will have two components of strain. One is the strain due to axial force at the level of tendon A, and epsilon C2 is a strain due to bending at the level of tendon A. Right. Now, what is epsilon C1? Epsilon C1, the force that what I am applying is on the tendon B. So, the force is going to be PB, right, and PB by A will give me the stress axial component, that divided by EC will give me strain. So, strain is nothing but stress divided by elastic modulus. So, that is what we have written, epsilon C1. The epsilon C2 is tricky. Now, what is epsilon C2? Epsilon C2 comes from the bending component. Now, bending component, how do you get your stress? Stress is nothing but M by I into Y. Now, what is this M? M is a bending moment due to pre-stressing. Now, what is the bending moment at pre-stressing? Now, when I am applying the force on the tendon B, the moment that is happening is from PB times EB at a distance of x, if I am looking at a distance x. So, that is your bending moment. Now, what is Y? Now, I am calculating the stress at the level of the first tendon. So, that is going to be EA of x, right. So, that is what we have here. Now, that divided by I will give me stress. Now, what is that I need? I need strain. Strain is nothing but stress divided by elastic modulus. So, you can see here, if you plug this, this is nothing but your stress, and this EC is, when you divide by that, you will get your strain. Now, because this bending moment and the cable profile A is changing at every distance x, so I can integrate the entire thing, okay, and get an average strain or average deformation, that when I divide by the length, overall length, then I get my average strain due to bending component, right. So, this is how we get your epsilon C2. So, this is your epsilon C2. This is an average strain component due to the bending at the level of tendon A. So, now when I add all of them, I will get epsilon C1 plus epsilon C2, then I multiply by elastic modulus will give me my stress lost, right. Okay. So, these are the things that we have already explained, and PB is the pre-stressing force in tendon B, L is the length of the beam, and EA and EBX are eccentricity of the tendons A and B from the left end. I is the moment of area of the beam, and delta L is the change in the length of the beam. So, you can see definition of strain is the overall change in the length by original length L, and the change in length is nothing but strain into small distance dx, that we are doing the integration to get your strain, right. So, this is the way that we get your epsilon C2. Okay, so, when you plug in all these profile equations for EB and EAX, finally, we can get this nice expression that can be directly used for calculating my epsilon C2. Now, if you give me the force PB and EA1, EB1, EB2, EA2 and plug into all this thing, directly I can get my epsilon C2. So, we have done the integration, and directly you can lead to this simple equation for your epsilon C2, where directly you plug in your eccentricities of the two cables and the pre-stressing force of the cable B, that what we are applying to get your bending component strain epsilon C2, right. Okay, so, now let us quickly look at one example problem and see how do we calculate the elastic shortening. So, we have an I section which is a pre-stressed concrete beam with a 500 mm by 1000 mm, and it is a pre-tensioned, okay, it is a pre-tensioned system using 10 12.7 millimeters. So, basically it is a 10 half-inch strand, okay, 10 half-inch strand, and they are stressed to 75% of it ultimate strength. I know this is FPU, and FPU is nothing but 1860 megapascal, right. And the strands are straight with 100 mm eccentricity from the bottom, and the clear cover is 50 millimeter, and we have to estimate the percentage of loss of pre-stress due to elastic shortening, and the modular ratio is already given to you as 7. So, let us look at now. This is a cross section, and typically in bridge girders, the section will not be, this is a simplified cross section that we have given. Typically you will have chamfers and all. This has been idealized into a simple I section like this, with a flange width of 500 mm and flange thickness of 200 mm, web thickness of 150 mm, and you have 10 of these pre-stressing strand. They are placed and they are CGS. The average CG of all the strand is going to be at 100 mm from the bottommost location. So, these all these details, the cross section has already been given. We are going to calculate now what is the elastic shortening loss. Okay. So, these are the cross sections areas. So, the AG is 290,000 millimeter square and gross moment of inertia is 3.536 into 10 to the power of 10, and this is a symmetrical cross section. So, the distance of the horizontal centroidal axis is going to be at 500 mm from the bottom. Okay. It is a symmetrical cross section. Overall depth is 1000 millimeters. So, YC is 500 mm from the bottom. Now, let us look at approximate solution. So, as you can see, we have already derived an expression for approximate solution. What is that we do? We know what are the initial pre-stressing force. So, we use only the actual area of the cross section, not the transformed area, right. So, let us look at now. The first we calculate the stress diagram due to the initial pre-stressing force, which is Pj by A. Now, what is Pj? And we can calculate the Pj, and then the next is going to be the bending component, and you can see here that this is your this is going to be in due to pre-stressing, this is going to be in tension, this is going to be plus, and this is going to be negative, and this is negative because of the pre-stressing. And finally, you will get the stress. The entire thing we are assuming that it is going to be in compression. Typically, that is how it will be, right. Again, this plus or minus comes depending upon whether you are looking at bottom fiber or tension fiber, it can be plus or minus. That is the reason combinedly it is written like this. Okay. Now, we have done this. So, what is the area of pre-stressing steel? And we know half inch, typically half inch strand is 12.7 millimeter diameter, and the area of this you cannot directly put pi by 4 into d square, because these are 7 wire strand. Okay. So, the area of this is 99.7 millimeter square. So, it is not pi by 4 d square. So, please keep in note, because the 7 wire strand there will be lot of gap, right. So, I cannot directly use the diameter for calculating the cross sectional area. You have to use the measured area, which is your typically for half inch strand it is 99.7. So, the area is 997 mm square, and the initial pre-stressing force is 0.75 times 1860 times 99. So, it works out to be 1390.8 kilonewton. So, this is the force, and eccentricity is 500 is your CGC, and eccentricity is 100. So, eccentricity is going to be 500 minus 100, which is 400 millimeter. Now, let us again look at stress. Now, how do we calculate? We have to first calculate the stress at the level of strand. So, elastic shortening is happening at the level of strand. So, we are calculating, so the stress at the level of strand. So, this is your axial component, this is your bending component. So, when you plug in your numbers, now again what is eccentricity is 400, and why we are taking 400? Because we are calculating the stress at the level of strand. So, YB is nothing but your E itself, okay. That is the reason we are putting 400. So, you get 4.79 and 6.29, and then you get 11.08 megapascal, okay. Now, we know that if I am talking in terms of stress, you have to multiply that M into FC into AP is your nothing but your loss and pre-stress. So, modular ratio is 7, FC is 11.08, area of pre-stressing this thing is 997. So, you get your force loss due to elastic shortening is 77.35 kilonewton, right. This is from approximate solution. So, in approximate solution we use only the gross area, right? It is a gross area. The actual area of the section is what we use. We do not use a transformed area, right. Now, let us look at percentage loss here. If you look at it, it is 5.56%. The initial pre-stressing force was 1390.8 and the force loss is 77.35. When you divide by that, you get 5.56%. Now, let us look at the accurate solution. In accurate solution, the difficult part is to calculate your transform section properties. You know, if you remember, we were using transform section properties. So let us look at that. Now, what is even? So, let us look at this. I have this entire section I have transformed into AT. Now, what is AT? AT is your gross area, right, plus A1. What is A1? A1 is, if I lump all the, see this white colored dot, what it shows is I have removed the area of the pre-stressing steel and I have converted into an equivalent concrete area. That is what I am putting it half of this. You know, if I take A1 is nothing but converting this AP into equivalent concrete area, right. So, which we will see. Okay. Now, minus this AP, right. So, so if you see here, the gross area is 290,000. So, this is the actual area, that is including, we are already including the area physics. What is A1? A1 is 6,979 millimeter square, which is basically modular ratio 7 multiplied by AP. So, this is your AP and this is your modular ratio. So, that we are defining that as A1, right. So, this is converted as an equivalent circle of 95 millimeter for moment of inertia calculation. So, what we have done is this transformed area of the bottom steel is converted into an equivalent steel of diameter of 94.265 millimeter, right. Now, this the actual gross area plus A1. In this gross area, we have already included this area of pre-stressing steel. That is the reason again I have to subtract this AP, right. So, because this is when this is getting replaced with concrete, that area I have to subtract it, right. So, this AG plus A1 minus AP is nothing but your transformed area. So, then you get your transformed area as this much. Now, again for this particular cross section, we should also calculate the centroid of the transformed section, and using your fundamental principles you can calculate. Let us say if I am taking the reference axis as the bottom, then you can find that if you go back to this cross section and if you take this as your bottom, right, then you know this cross section areas and you can calculate your CG for the transformed section for this as a reference axis. Okay. Now, let us see how do we get it. This is basically, and this is basically, this is going to be at a distance of 100, and what is the diameter? This is 94.265 millimeter. So, let us look at it. Now, you see here A into 500, the overall area is the CG for that area is going to be 500, and A1 minus AP is going to be at 100, okay, this is divided by the overall area. So, if you do that, you get your centroid of the transformed section is 491.92 millimeter. Now, previously, you know, when we do the simple cross section, it is 500 we took, right. So, for then again moment of inertia for the transformed section, you can calculate. Let us look at this. For moment of inertia of transformed section, again you can see moment of inertia of the gross section AG, and then parallel axis theorem, area of the section multiplied by the distances of their CG square. Okay. For AG it is at 500, for transform section it is 491. So, area into the differences in their CG square using your parallel axis theorem. So, this is from your parallel axis theorem. Then I of your A1, which is your transformed equivalent bar, which is this, right. So, this is basically this two component is nothing but for this, and this IA1 is for this, and this is basically plus IA1 plus the A1 into the distance square is for this, these two things are for this, maybe I should, okay. This is for this, right, and this is for this, okay. So, for each of this component using parallaxes theorem, you calculate the respective moment of inertia, and then these two has to be added because I have to deduct this area because this area is already included in the A1. So, that is the reason this is becoming minus, right. So, when you do all these things, you get your transformed moment of inertia as 3.661 into 10 to the power of 10, and this is the value that we need to use, okay. Now, again this A1 we know that we converted as an equivalent circle of diameter 94.265 millimeter for moment of inertia calculations. So, when you do that you see that again the process is same, we are calculating the stress at the level of strand. Now, only thing is we are using now the modified your eccentricities from the transformed cross section. Again area also here you see here it should be actually 80, right. So, 295,982 and the force remains same 1390.8, and then the moment due to pre-stressing is this multiplied by eccentricity. So, this eccentricity originally it was 400 in a simple calculation, now it is 391.92. So, the difference is not really much, it is about 8.0208 millimeter, which is not much, right. And again this is at the level of y, which is equal to E again, and then your moment of inertia of transformed cross section is 3.661 into 10 to the power of 10. So, if you plug in all the numbers, you get the stresses negative 10.535 megapascal, and then if you substitute the loss and pre-stress as 7 into modular ratio times your stress multiplied by area will give me this force, and percentage loss is this into 100, which works out to be 5.28%. So, if you see the difference between the approximate solution and accurate solution is not really very significant, okay. The approximate solution is actually conservative, okay. In fact, in losses it's always better to be a little conservative in estimation, so that you do not have any cracking or deflection issues, but at the same time it should not be too conservative also. But here you see here the difference is not really much, they are nearly same, but for accurate solution I have to calculate your transform section, that is the difficult part, right. So, you ended up, so with this we can see that just calculating the stress using gross sectional properties is good enough for calculating the elastic shortening, right. So, these results again shows that gross section property can be used instead of transform section property for easy calculations, because the difference is not really much.